Well, friends, welcome to my class on the computational method to explore rotational spectra. Uh, Friends, you have your experiment paper, uh, and the code of this paper is 5505L. Here, L stands for your experiments. In this paper, you have to perform several computational exercise, and we will discuss the first exercise of the paper physics 5505, and your first exercise is based on uh, rotational spectroscopy, and you have to explore a rotational spectra. So basically you have to develop a computational exercise using your Excel sheet to explore rotational spectra. You have to select one diatomic molecule, and I will show you the method how you can explore the rotational spectra of a given diatomic molecule to you. Friends, you know that there is a transition between the rotational levels among a given electronic state, and this transition gives rise to a pure rotational spectra, and these spectra are observed in a far infrared region we consider as a microwave region. And if you find the wavelength of the rotational lines, you will find of the order of 10 raised to 2 micron to 10 raised to 4 micron. The study of such transitions it provides a direct method for the evaluation of molecular parameters. The most important information that you get from the rotational spectra is determination of a rotational constant, rotational energy spectrum, intensity of rotational line, relative population of the molecule in different rotational states. The basic goal of this exercise is to provide you a computational exercise, basically undergraduate students, to evaluate the molecular parameters of a diatomic molecules. And I'm sure that this computational exercise will help you to understand the rotational spectroscopy in detail, and this exercise is making the learning more interesting and innovative. So I would like to explain you the method and the procedure that how you have to prepare an exercise for a diatomic molecule. Generally, you know that the molecular requirement for obtaining rotational spectra is you should have a polar molecule, a molecule which possesses a permanent dipole moment will give you a rotational spectra. Of course, it will also give you a vibrational spectra. So first of all, we would like to explore the rotational spectra. So the basic objective is you have to compute the wave number frequency, right? You have to calculate the wave numbers of the rotational spectra of a diatomic molecule. That means you know that you get a series of dark lines. I know that you have already studied the rotational spectra in your theory classes, and you know the features of a rotational spectra, that it consists a series of dark lines which is already, I mean, which is almost equally spaced, and the spacing between the rotational line is constant. So here you people have to find out the wave number of each rotational line, as well as the energy of the rotational energy levels, and you have to also find out the number of molecules present in various jth level. You have various rotational level, as you know that you have already studied, that you have a rotational energy level E0, you have a rotational energy level E1, E2, E3, E4, where that 0, 1, 2, 3, 4 we basically describe the quantum number. You have for j equal to 0, you have the lowest rotational energy level which we consider as E0. For j is equal to 1, which we consider that it is a rotational energy level E1. So you have to find out that number of molecules accumulated at the level zeroth level, or number of molecule which is present in the level number 1, that is the first excited level of rotational energy level, that we will calculate. Here you see the input parameters. You see the primary parameters such as the mass of the molecule, which we consider as a reduced mass, the bond length, and the force constants of the molecule will be given to you. So when you set up this exercise, you have to select one diatomic molecule. Either you can select, let us say, hydrogen fluoride, or you may select HCl, you may select HBr, or you may select some other diatomic molecule which is known to you. Here I have selected a molecule HF because some experimental evidences are also available with us. So when you calculate the rotational spectra, or when you calculate the rotational energy, or when you calculate a rotational constant, or the wave number of the rotational line, you can compare your result with an experimental finding. So when you compare your result with an experimental finding, you will see that the result which you are getting using the Schrodinger equation and using the rules of quantum mechanics here are in a good agreement with an experimental finding. So this will help you to understand the role of quantum mechanics to understand the molecular spectroscopy. Okay, so this exercise will help you to understand the applications of quantum mechanics also. So let us start the session. You know that first of all, you consider your molecule as a rigid rotator. And here you consider that the distance between the two dissimilar atoms, you see the atom M1, that suppose if I consider the hydrogen fluoride, suppose this M2 is a hydrogen atom, and then M1 will be the fluoride atom. And this is the center of mass, and this is the internuclear axis, you see. And you see this is the axis of rotation here. Here both the atoms are rotating about an axis which is passing to the center of mass, and it is normal to the internuclear axis. So this is the model which you have selected. You have selected a rigid rotator where the distance between the two atoms is constant, it is rigid, that is R1 plus R2 is equal to R, that is known as the bond length. Here you consider the bond length constant, and you see, that is the R is constant, and you write down the Schrodinger equation and you find the energy eigenvalue, and ultimately you calculated the rotational energy of the atomic molecule for various quantum states. So here you see this equation is known to you. Energy, rotational energy equal to h square upon 8 pi square I j into j plus 1, where j is a rotational quantum number which is quantized, and the possible values of j is already, you know that it is 0, 1, 2, 3, j equal to 0 is the ground state, and you have the energy level is known as E0, then j equal to 1 it is E1, E2, E3. So first of all in this exercise is that you have to calculate rotational energy. So generally, when you calculate energy in a rotational spectroscopy, you calculate the energy first in erg or in joule. Then you convert the energy into electron volt. And generally, you know that whenever you write the rotational spectroscopy or a vibrational spectroscopy, we generally write energy which is calculated in terms of wave number, because that we have already discussed, and you know that energy is given by h nu, or you can write down it is hc by lambda, right? So using the conversion factor, one can write energy is calculated in terms of wave number units. Energy is calculated in terms of wave number units, that I will discuss when we solve the Excel sheet. I would like to discuss this problem with the help of Excel sheet. Of course, there are certain students in this classroom, they are familiar with a C language, or if you know the Python language, you write a computer program and obtain the required parameter and required values using computer program. Or those who do not know the programming, you please write and prepare an Excel sheet and obtain the required rotational energy levels, as well as several parameters which we will discuss today. So you know that the first thing is you have to calculate the rotational energy, and you have to obtain the rotational energy levels, and you have to show that rotational energy levels are not equally spaced. So first thing is that you take a molecule, suppose you take the molecule HF molecule, and for the HF molecule you have to take the input parameters. So you see, I will show you the input parameters are mentioned here. You see, this is your molecule HF. The input parameter is given, the mass of hydrogen atom is given here in terms of atomic units, mass of fluorine atom is given in atomic units, its force constant is given here. So these input parameters you have to select. Of course, it will be given, and to remember the bond length of HF molecule is also given to you. It is 0.927 angstrom unit. You may select HCl also. Uh, there are two cases, but when you take HCl molecule, then you have to go for a literature survey to compare your result with an experimental finding. Because we have already experimental findings are available for HF molecule in the literature. So the values are given. I will give you the experimental finding. So whatever the result you calculate using your Schrodinger equations, you can compare with an experimental finding, and that will help you to understand the rotational spectroscopy in detail. So friends, you see, first thing is that you select the molecule, calculate its energy eigenvalue, and find out the energies, rotational energy for various rotational quantum states. And you see that once you see this, so these are, you have calculated E0, E1, E2, E3. These are all rotational energy levels. And you see that you have the possible selection rule, that means that transitions takes place between a lower rotational quantum state to the upper rotational quantum state, but it does not take place arbitrarily. Right, there is a selection rule, there is a quantum mechanics which governs the transition among the rotational level. Here I will not describe how you obtain the selection rule, when you refer your textbook, uh, uh, you can find out the selection rule for absorption is delta J equal to plus 1. So when a molecule jumps from the rotational constant 0 to 1, there is a transition. This transition is allowed and delta J equal to plus 1, right? Or a molecule which is in the upper state, when it goes to the lower rotational state, from where there is a downward transition, there is a transition from J equal to 1 to J equal to 0. This transition is basically known as delta J equal to minus 1. It's basically emission spectroscopy. Generally, rotation spectra are observed in absorption. So we take delta J equal to plus 1. So you see there is a one transition. This transition is allowed. This transition is allowed. This transition. These are the allowed transitions according to delta J equal to plus 1. And each rotational transition, these transitions, you see there is a one photon is absorbed. The photon which is absorbed as appears as a dark line, and the wave number of that line is 2b, where b is a rotational constant. I will tell you how to find rotational constant here. The next possible transition is from j equal to 1 to 2 is the wave number of that transition, that line is 4b, 6b, 8b, 10b. So you can see that the rotational lines, you get a series of dark lines here, and these dark lines are observed in far infrared region. If you measure the wave number of this line, the wave number of this line will fall in that microwave region. Far infrared region is almost coinciding with the microwave region of electromagnetic wave. So this we have to observe. You see, when you are doing this computational exercise, this you have to compare, and you have to find out that when you get the first rotational line, find out its wave number, find out its wavelength, and verify that whether this line is in far infrared region or not. This will help you to explore the rotational spectra, to explore your microwave spectroscopy, and to understand the concept of you see the molecule is a polar molecule, and the requirement is that it possesses a permanent dipole moment. So here with this, you see, you can have the wave number. This is basically the expression for a rigid rotator which you have considered. My dear friends, you see there are two models which you have considered. The wave number of this line, right, is given by this expression 2b j plus 1, where j is the quantum number of the lowest rotational states. Suppose if there is a transition from 0 to 1, so you have to take j equal to 0. If there is a transition from say, let us say, from 1 to 2, so then you have to take j equal to 1. This is already discussed in your class. So you put j equal to 1 here. So you will put 1 here, so 1 plus 1 is 2, 2 to 4b. So you can see this is 4b. Similarly, you have a transition from 2 to 3. So when you have a transition from 2 to 3, you have to take j equal to 2 in this expression. And this you can see. So dear friend, you see, basically you people have to use this formula and find out the wave number of each line, right? And compare this result, the wave number which you calculated with the help of a rigid rotator, and then you have your model which is a non-rigid rotator when molecule is rotating, and because of this centrifugal force, both the molecules you see experience uh, because of centrifugal forces. You see the bond length, this distance r is not remaining constant, and there is a change in distance r, right, where r is not fixed. Both the atoms are slightly moving away. Uh, So because of that, here in case of a non-rigid rotator, the distance r1 plus r2, that is not remaining constant. It is slightly changing because of the centrifugal force. So here you see this expression which I wrote here. This is the expression. It is also derived in your textbook, where this constant d, you can see it is known as a centrifugal distortion constant, and you calculate the wave number of a non-rigid rotator, you calculate the wave number of a rigid rotator, and compare your result with an experimental finding, and you will see, you will conclude that in practice your molecule is not basically behaving like a rigid rotator, but because of that centrifugal distortion, you will have a model which is considered as a non-rigid rotator, and your result, whatever you will get, the wave number using a non-rigid rotator, when you will calculate this result, will be very similar to the result of this. Okay, so now let us understand the result. So before I understand the result, uh, let me share one file. So just give me a minute, I will share my file. Look at the file here. I have prepared an Excel sheet to demonstrate how do you calculate the result. So you see in the first column, I consider the HF molecule. So here I consider the mass of hydrogen atom. I consider the mass of fluoride atom. I calculated the reduced mass using the expression, because if this is a mass of hydrogen atom is M1, mass of fluorine atom is M2, so I can calculate by M1 into M2 divided by M1 plus M2. So I calculate reduced mass in atomic unit, and then you calculate your reduced mass in gram. So there is a conversion factor which you have to use and convert your reduced mass into the gram. The bond length is given, and then you can calculate the moment of inertia of the molecule, of which is the molecule which is given, that HF molecule. So you can use I equal to mu r square, where mu is a reduced mass. So you calculate your this, and then you see this is the Planck constant, this is the input parameter, and then I calculated, you see here the rotational energy. Look at this. I calculate the rotational energy for quantum number j here. So I calculate the energy. The first rotational energy equal to 0, right? It is basically h cross square upon 8 pi square I into j plus 1, where j is 0, so energy is 0. So you have a 0 energy. This energy I calculated, you see, in org. Then for j equal to rotational quantum number 1, I calculated the rotational energy in or you can see that is 8.10 raised to minus 15. The same energy I have converted into the electron volt, and now I convert my energy into the wave number units. So what you do, you divide by E by Hc, right? And that you can see I calculated the wave energy in terms of wave number, and there is a conversion factor which you can verify, that 1 electron volt represent equal to 8066 centimeter inverse. This is the conversion factor. 1 electron volt corresponds to 1 electron volt of energy corresponds to 8066 centimeter inverse. This is the conversion factor which is given in your textbook. So look at this. I calculated the rotational energy here. The rotational energy I calculated for each rotational quantum state, j equal to 0, j equal to 3, j equal to 4, j equal to 5. And you see, I have calculated the rotational energy for energy in org. I have calculated rotational energy in electron volt. I have calculated the rotational energy calculated in terms of the wave number unit. So this is the wave number unit. You see, I calculated the rotational energy, and these rotational energies are in centimeter inverse. You see this. So this is you have to understand uh, conversion also. And now you have the term value which is already mentioned. You see the equation which I said, the term value of each rotational level. The rotational level j equal to 0, the term value is 0. The rotation number j equal to 1, term number is 2b. The rotation number j equal to 3. You see rotational level j equal to 2, its term value is 6b. Rotational level j equal to 3, its term value is 12b. Rotational level j equal to 4, its term value is 20b. And you see, you compare this, and you have already calculated your rotational constant here. The rotational constant is already calculated. So you can see, you can compare, this is 2b, right? This is the rotational constant is given here. These constants are given. This is 2 times, this is 20 centimeter inverse, right? So please concentrate this, that for j equal to 0, of course, rotational constant is constant for all the rotational levels. So here you can find out the rotational constant, and once you know the rotational constant, you can compare your term value. I mean to say that for j equal to 0 rotational energy level, the term value is 0. For j equal to 1, the term value is 2b. For j equal to 3, the term j equal to 2, I'm sorry, j equal to 2, the term value is 2b. So what do you have to compare that? Are you getting, for suppose j equal to 1, you see the value is, it should be equal to 2b. So you see the b is equal to b, rotation constant is 20, which we have calculated. And now you compare this is 2b, so it is 20 into 240, so it is of the order of 40. So you have to verify the term value, right? That is the wave number. Basically, energy calculated in terms of the wave number, which is known as a term value. So the term value of each rotational energy level, you see, this is the term value for a rotation quantum state j equal to 5. For j equal to 5, it should be 30b. So b is 20, which we have already calculated here. So 20 into 30, that comes out to be 600. You see that value, there is an agreement here. So you have to prepare a Excel sheet here, put your parameters, work out your exercise, and find out the rotational energy level. You see, I have calculated my rotational energy level. This is the rotational energy levels, and I calculated the rotation. These are my rotational energy levels. You see, this is for j equal to 0. I calculated the energy E0. J equal to 1, I calculate the energy E1. J equal to 2, I calculate the energy level E2. J equal to 3, I calculated the energy E3. J equal to 4, I calculate the energy level E4. So these are the rotational energy levels. And these are the various rotational energy corresponding to each quantum state. I calculated in erg, I calculated in electron volt, I calculated in centimeter inverse. You can calculate it in meter inverse. And first you calculated the energy in electron volt, and then you convert the energy into the wave number unit. So whatever the energy you calculate, divide by hc. See what the energy you divide by hc, that will give you the energy in wave number units. So this exercise will give you several concepts for calculating the energy in various units. You see, generally we write our energy expression in terms of wave number units. And am asking you that you please derive this conversion factor, that if you have the energy of the incident radiation, let's say of the order of 1 electron volt, what will be the corresponding wave number of that radiation? And that radiation is equal to, suppose if you have a energy of the incident photon or emitted photon whose energy is 1 electron volt, what will be its corresponding wavelength? So the corresponding wavelength or wave number will be of the order of 8066 centimeter inverse. So this you please prepare an Excel sheet, work out this and compare your result. And now you want to compare this result with your experimental finding. So let me share another file. Just give me 1 minute. Okay. Here you can see now the result which we have calculated. So we have HF molecule. We have calculated the rotational constant theoretically using the Schrodinger equations. We have calculated and compare with an experimental finding. Look at this. This is the result which we have computed. This is the experimental finding. This is the rotational distortion constant D, which you can calculate using this expression. The rotational distortion constant D, which you can calculate using this expression, which is I have given to you, right? You calculate this and compare with an experimental finding. Find out its fundamental frequency of oscillation using the expression you see 1 upon 2 pi into bracket into the a term you have a square root of k divided by mu. You have a fundamental frequency of oscillations. Of course, it is not required here only. We are basically interested for a rotational spectra. We are not at all interested the vibration of this diatomic molecule. But this is a fundamental constant. Generally, we ask students to calculate this fundamental frequency of oscillations. So this is basically a centrifugal distortion constant you can calculate. You can compare with experimental finding. You have a rotational constant. You can compare with an experimental finding. These are the input parameters which is known to you, which is given to you. I have used this reference 6 and reference 3. These are the two several textbooks, which is very important textbook, which is also giving you some experimental results of certain molecules also. So you may refer. I will give you this reference 6 and reference 3 after completing this exercise. You see here, these are the result which I have calculated using basically writing a small program. Here also you can prepare a program, or you may write Excel sheet, and you have a transition from J to J to J plus 1, that is 0 to 1. I took the transition from 0 to 1, whose wave number is 2B. I calculated for rigid rotator. I calculated for non-rigid rotator, and there is an experimental wave number which is I found it from reference number 6. You can compare this result. You see, this is for rigid rotator, this is for non-rigid rotator, and this is for your experimental finding. You will see that your results for this is the transition from 2 to 3, delta j equal to 1. This is also delta j equal to 1. This is delta j equal to 1. You see your results are 204.80 centimeter inverse. Your results, almost your results are close to the non-rigid rotator, right? You can see your results uh, 439 and this is 441. So when you compare the result, you will find that the result of a non-rigid rotators are in good agreement with an experimental finding. Of course, I would say that these rigid rotators are also in agreement, but there is a good agreement of the results of a non-rigid rotator with an experimental findings. So this will help you to understand the concept of a centrifugal distortion constant d, which we have introduced for calculating the wave number of each rotational level for the case of a non-rigid rotator. Look at the result here and look at these results for the rigid rotator, non-rigid rotator, and the experimental findings. So this you prepare with the help of Excel sheet, no problem, or you may write a small program also and find out these experimental findings. I'm sorry, find out these findings of rotational say rotational transitions and compare with an experimental findings. I will appreciate that if you write the Excel sheet, that will be very nice, and prepare the chart, prepare your report here. And now you have another exercise which you can work out. This is giving you a relative populations of the molecules in a different states. That means number of molecules present in the Z state relative to the number of molecules present in the ground state. This you can calculate using the Boltzmann spectra, and these derivations are given here. So you see the number of molecules present to the jet quantum state related to the number of molecules present in the ground state is given by this. So here you can see it is basically temperature dependent term. This KT is a Boltzmann term. So here you have to explore the relative populations of the molecule at various temperature, and you have to plot this graph for a various temperature. So I have prepared this graph for HF molecule, and you can see I have calculated the relative population of the molecules in a various states at different temperature. I calculated the relative population, that is the ratio of Nj to the N0 at 200 degree Kelvin. And look at the curve, you see that Ng by N0 increases initially, reaches to maxima, and again there is a fall. And you can see that the peak of the curve is shifting towards the higher quantum number as temperature increases. So this will also explain you the physics that rotational level of a diatomic molecules are fairly populated. Please remember this. And you know that the vibrational levels of a diatomic molecules are not at all fairly populated. The lowest vibrational state of a diatomic molecule is highly populated because the spacing between the vibrational levels, which you will calculate, the spacing between the vibrational level is greater than the energy possessed by the molecules at room temperature, and it is basically a thermal energy. Thermal energy is of the order of kT, and you see that generally when you see the graph here, the spacing between the rotational level is almost 2b, 0 to 1. On here it is 4b between these two levels. So if you calculate 2b, when you calculate b in terms of centimeter inverse, and you multiply by 2, b in this case our b is almost 20 centimeter inverse. So 20 centimeter inverse into 2 is 40 centimeter inverse between. So the rotational energy spacing between the two rotational level is almost 40 centimeter inverse. And this 40 centimeter inverse corresponding, you calculate this energy, right? Because E by Hc is the conversion factor. So when you calculate this energy in terms of that, if you calculate the thermal energy, so thermal energy possessed by the molecule is kT. So your kT is almost greater than 2b. If you compare, you please work out this exercise, that the thermal energy possessed by the diatomic molecule at room temperature is kT. And if you calculate the spacing between the two rotational level, that is j equal to 1 to j equal to 0, that is delta j, that this energy, that energy is 2b. B for HF molecule is of course of the order of 20 centimeter inverse. So 20 centimeter into 2 is 40 centimeter inverse. This 40 centimeter inverse, you calculate energy in terms of electron volt using the conversion factor. So you will find that kT is greater than the spacing, that is 2b. So at room temperature, you will find that the upper rotational levels are fairly populated. Even if you calculate 4b also, this spacing 4b, 4b is also, if you calculated its corresponding energy in electron volt, your kT is also greater than 4b, that you will find. So the upper rotational levels at the room temperatures are fairly populated, and this relative population is a very important term. You see, as temperature increases, the peak of the curve is shifting towards the higher quantum number. You see, when you calculate it, and here you have to find out for which quantum state J, which is highly populated. Suppose if you are working at the room temperature 300 degree Kelvin for HF molecule, you can find out that this is the quantum number. That if you find out this is the quantum number which is highly populated, this is the rotational state which is highly populated, and that can be done with the help of simple expression. You have this expression, you differentiate this expression with respect to j and keep it equal to 0. You will find out the rotational quantum state j, which is highly populated, which is the maximum quantum state, maximum value of j, which is highly populated. You can verify this expression, differentiate with respect to j, and put j equal to 0, because at this point the slope of the curve is 0. Here you to calculate d by dj of nj by n0. So here you will find out the value of j. So if you see at 300 degree Kelvin, you will find out that for HF molecule, for room temperature 300 degree, your rotational quantum number, suppose if you draw a normal year, you will find almost 3. So rotational quantum number 3, or I would say quantum number 3, is highly populated. So here you see this particular graph is basically giving you a temperature effect on the diatomic molecules, as well as you will see the relative populations of molecules in a various state at various temperature, and you have to plot this graph for HF molecule for this temperature which I have given. You draw the graph for 200 degree Kelvin, 300 degree Kelvin, 500 degree Kelvin, and 1000 degree Kelvin, and find out the value of J at which the rotational level is highly populated. So this is an exercise which you people have to perform, and you have to prepare your Excel sheet, or either you can write a small program and find out this result and prepare your report and write down the concluding remark. So this is an exercise. This exercise will help you to explore the rotational spectra. So this is a computational exercise which we have basically developed to explore the rotational spectra. And once you understand, and once you see this exercise will make you, exercise is making your learning more interesting and innovative. And basically, this exercise is to provide you a computational exercise to evaluate the molecular parameters of the diatomic molecules. So here I request you all of you select HF molecule, right? The input parameters are given. So you take these input parameters, prepare your Excel sheet, or write the Fortran code, or your C language code, and find out rotational constant, find out rotational distortion constant, find out its fundamental frequency, then you find out the rotational spectra and you find out the rotational energies. You find out rotational energy of various rotational quantum states. Find out the wave number of each absorption line which you obtain in a rotational spectra in far infrared region. Compare your result with a non-digit rotator. Compare your result with an experimental finding. Then you find out the relative population of the molecule for the different states. Find out the value of J. Write your conclusion and prepare the report for this uh, exercise for a rotational spectroscopy and explore the rotational spectra. I hope you will perform this exercise and you will submit your report, right? Because you have to prepare your journal and you have to write this exercise in your journal also. So I request you perform this method to explore the rotation spectra using Excel sheet and do the needful. Thank you very much.